All right, welcome back, everybody. Today we're going to be getting into some really cool stuff. We're on to section 11.8, which is all about power series. The last few sections of this class are just really amazing, and all of the ideas that we learn here, just you use them forevermore, forever after. They're just really cool ideas. I always say that you want to ask yourself, why do I care about this stuff? Why am I learning about this stuff? Of what use is it to me? Why should I care? We're about to get the answers to those questions in the next like three sections right here. This is kind of the culmination of everything, the next three sections right here 11.8, 9, and 10, and 11.11 too, which is like a specific application. So let's jump right into it. So we're going to talk about a very particular kind of series now. And we're going to focus on this type of series and some other very important types of series for the next few sections. For now, we're going to talk about what are called power series. Uh, I'll say this too, this is actually going to be relatively short, but this is a critically important section. I know a lot of my students that end up taking diff-EQ, differential equations, they'll often ask me if they can have my slides for this section because power series and Taylor series come back in such big ways in differential equations and beyond that you do need to have a deep intuitive understanding of them. So I hope I can help you develop that through these lectures and through our activities and so on. So we're going to talk about power series, and we're going to talk about their radius and interval of convergence. So let's start with just the definition. um, so what is a power series? A power series is a series of this form, just like that. Here's what it looks like in expanded form. Here, x is a variable, and the c sub n's are constants called the coefficients of the series. So if I go back to this for just a minute here, this is c0 times x to the 0, which is 1, c1 times x to the 1, c2 times x squared, c3 times x cubed, c4 times x4, and so on. So what's going on here is we have some constant coefficients, and then we have a variable x that's being raised to a power, right? Now here's the cool part. This series, this power series, it may converge for some values of x and diverge for other values of x. So the convergence and the divergence of this series depends on x. And here's what's even cooler about this. If it does converge, then the sum of the series is a function. It's a function of x that we can write as the actual sum of the series. So as long as the series converges, it defines a function. And we can define the series as that function, which is pretty amazing. What's the domain of the function? The domain of the function is the set of all the x's where the series converges. That's the domain. Wherever it converges, that's the domain of this function. So, or in other words, the function is undefined for values of x for which the series diverges, right? So that's what a power series is. Here's a couple, or here's one simple example, just x to the n. Add up all the x to the n's. That's equal to 1 plus x squared plus x cubed plus x to the fourth. All right, that's a power series. When does it converge? Well, this is actually not just a power series, it's also a geometric series. It's a geometric series, which we know converges when r is less than 1 in size. In this case, r is x. So whenever the size of x is less than 1, the series will converge. This series will converge. Otherwise, it will diverge. It'll diverge. And that's it. Yeah. So as long as x is between -1 and 1, we have a well-defined function written as a power series. Pretty wild. That's what it is. So this is where things start to just blossom, and there's all this possibility that comes out of these ideas because you can start defining functions as series as long as the series converge. And this is why we spent so much time investigating series like sections 11.1 to 11.7, learning all those tests, learning all those theorems, learning all those definitions, because you want to have a really comfortable understanding of what it means for a series to converge or not. Because if it converges, you might be able to define a function based on that convergence. So cool, so cool. Okay, more generally speaking, we can talk about power series that are centered at a number A. So a power series centered at A is a power series of this form. And the only difference now is that we've basically shifted the x's by a fixed number A. You could think of the original definition or the first definition here. You could think of these as power series that are centered at 0. Right? Power series that are centered at 0. So it would look like this. C sub n x minus 0 to the n. That's what this is. That's what this is. So this is saying that, hey, you don't have to have everything centered around 0. You can actually talk about a power series that is centered elsewhere, around a different number. Oh no, my Apple Pencil's going to die soon. I hope it lasts. Um, let's see. Power series centered at A. Oh yeah, and this is just the expanded form. So just writing out these terms, C0 times x minus a to the 0 gives you C0. C1 times x minus a to the 1 gives you C1 times x minus a. C2 x minus a squared. C3 x minus a cubed, and so on. I feel like I've said and so on 100 times now. All right, so here's a good question. We've got a potential power series here of this form. The question is, for what values of x does it converge, right? Let's think about it for a minute. Um, Again, it really, really does depend on x. So if I just look at this series on the surface and I kind of think about what it would look like if I plugged numbers in for x, like what do I get if I plug in 6? Like what if x is 6? All right, if x is 6, I get 6 minus 5 to the n, which is just 1 to the n, which is 1. So when x equals 6, what we get is this, which is the harmonic series which diverges, right? Okay, so it diverges there, but what about other values of x? Are there values of x for which it converges? Yes, there are. Let's find them. What we're going to use is we're actually going to use the ratio test. You don't always need to use the ratio test. You can use other tests, but this test is really handy for determining the convergence of power series. So remember that the ratio test says you want to look at the limit of this ratio and see what it goes to. So we're going to do the same technique that we used in the previous section, or section 11.6, I should say. Here's a sub n plus 1, a sub n plus 1, I should say. Here's the reciprocal of a sub n, so I basically skipped writing the fraction and just multiplied by the reciprocal. Now I'm just doing some algebraic massage, canceling things like I did before. I've got x minus 5 to the n, x minus 5 to the n, and so I'm left with 1 x minus 5, and I'm just kind of moving things around. So what I'm doing to go from here to here is recognizing that n over n plus 1, that's always positive, so its absolute value is just this again. But we don't know the value of x, so this absolute value applies to the remaining factor of x minus 5 that's left over, which is this. There we go. These are all in the limit, so this is really what we're taking the limit of. Now, again, we're just trying to evaluate a limit. But notice here that the limit operator only depends on n. So n is what we're sending to infinity, not x, right? It's n in this case. So we need to evaluate the limit of this thing as n goes to infinity. Use a classic use a classic limit technique, divide the top and the bottom by n, you get this. Now when n goes to infinity, this goes to 0, so this goes to 1, and so the whole limit goes to absolute value x minus 5. Okay, let's pause for just a minute here. This is saying that the limit of this ratio is equal to this value right here. Now the ratio test says that the series will converge as long as this thing is less than 1, and it will diverge if this thing is greater than 1. So let's investigate that a little more carefully. This is just what I just said. So this thing will be convergent. This series will be convergent when this is true. Let me write this up here. So what we need is we need this. We need x minus 5 to be less than 1. That's equivalent to saying this, which is equivalent to saying this. There we go. Just like so. And that's where I'm getting this. So as long as x is strictly between 4 and 6, the series will converge. It'll converge. Cool stuff. We also know that when the size of x minus 5 is bigger than 1, the series diverges. So it diverges if x is bigger than 6 or less than 4. However, we don't know what happens when that's equal to 1. So because we don't know what happens when it's equal to 1, we have additional work that we need to do. We need to test the endpoints. So we don't know what's happening at the endpoints yet. We have to test those specifically by plugging those endpoints back in for x in our original series and then determining the convergence of that resulting series. So sometimes it can get a little bit tedious, but this is why we spent so much time learning how to determine the convergence of series for the past 7 sections. Because now you probably have a lot more comfortability saying like, oh, that's going to diverge, that's going to converge. Now you're going to use that skill literally right here. So we're going to test the endpoints. Plug in the number 4, see what happens. Plug in the number 6, see what happens. Here we go. If x is equal to 4, then when I plug in 4 here, I'm going to get 4 minus 5, which leaves me with negative 1. This is the alternating harmonic series, which converges. It converges conditionally, but it converges by the alternating p-test. When x equals 6, this one we already did, right? When x equals 6, we get just the standard harmonic series, which diverges. Thus, our interval of convergence is the interval from 4 to 6, including the number 4. Including the number 4. There we go. So the ratio test guaranteed us absolute convergence on 4 to 6, and this additional exploration gives us convergence at the endpoint, at the endpoint 4 as well. So we got a little bit more convergence there. Okay, so what do I mean when I talk about the interval of convergence? Let's get some definitions for this thing here. This funky, messy definition, which we're going to clear up in a minute here. So now that we've kind of seen what a power series is, we have to talk about its radius and interval of convergence. So associated with each power series is a radius of convergence, r, and an interval of convergence. The number r, I'll say number in quotes, could be 0, any positive real number, or we can also define it as positive infinity. What is this radius, capital R? So you can actually show that the radius of convergence will be this number here, but you will not need to worry about that in this class. Math majors, you will need to worry about this later on because this is something that you're going to prove later on. This is basically the formula for the radius of convergence, but for our purposes in this class, in Calc 2, this is not a very helpful formula. However, I did want to include it just for completeness. So that is the actual formula if you needed a specific formula for it. If this limit is 0, then we define the radius to be infinity, meaning the radius is literally infinitely long radius. If this limit is infinity, then we define the radius to be 0. So sometimes the radius can literally be nothing. It could just be a single point where the series converges. All right? So that's the radius of convergence. In practice, it is easier to investigate the interval of convergence first and then determine the radius of convergence. So associated with each power series is an interval of convergence, and the interval of convergence is determined by the radius of convergence r and the convergence or divergence of the power series at the endpoints. The interval is always centered at A. That's why we call it the center. And the interval of convergence will always have one of these 4 forms. Again, this is not something you should memorize. It's really just trying to be complete and clear with what's happening. What this is saying is that your interval may be closed on both ends. Oops, I should say this. Closed on both ends, open on both ends, or it could be half open, half closed. That's all this is saying. That's all this is saying. And remember that R could be 0 and R could be infinity, right? It could be infinity. That's what this means. Okay, so do I say it here? Oh, I don't say it yet. I don't say it yet. I kind of mentioned it, but I'll say it again in another slide. All right, so here's the big theorem, and this is the theorem that gives us the hefty result that we've got here. Given a power series, there are only three possibilities. So if you've got a power series of this form, there's only three possibilities here. First possibility, the most uninteresting possibility, is the series only converges at the center. I said most uninteresting. I should just say least interesting. So if your radius is 0, that means your series only converges when x is equal to a, and that's just not a very interesting series. It may just converge at a single number. We've got another possibility. The series converges for every real number. That's when your radius is infinity. So when you have an infinite radius of convergence, you're saying that this series converges for all real numbers x. That's what you're saying. And then the third possibility is, hey, there's a positive real number, not infinity, like a real number, where the series converges absolutely if this holds, and it diverges in this case. Those are the three possibilities. That's pretty much it. That's pretty much it. All right, so you either get convergence at a point, convergence everywhere, or a specific finite interval of convergence. Those are the possibilities. Okay, what I'd like to tell students is this. In practice, especially in this class, it is often easier to find the interval of absolute convergence using something like the ratio test or the root test. It's easier to do that first and then determine the radius by just dividing the length of the interval by 2. So for each of these, like if you go, let me go back a couple slides here to that example. Yeah, so here in this example, we found the interval of convergence to be this. Let me highlight it, right? So the interval of convergence here is 4 to 6, including 4. The radius here is just 1, because what you do is you take the length of that interval, 4 minus 6, and divide it by 2. Which is 2 over 2, which is 1. The radius is half of the interval. That's really all it is. That's really all it is. So if you've got the interval, you know the radius. Just divide the length by 2. And that's what I'm saying right here. Commonly, it's easier to just do that. The other thing I want to say is this, because this is one of the things that I like about math. The word radius is a very, very intentional choice. And the reason is because when you're in 2 dimensions and when you're looking at power series in 2 dimensions, meaning there are 2 variables involved, then the basic region of convergence is a circular disk of a certain radius. Yeah, so rather than looking at intervals centered at A, now what you're going to do is you're going to look at literally like a circle centered at some point. Maybe I'll call it a bar or something like that. Let me zoom in a little bit. And then the radius of convergence is literally the radius of the circle. Oop, there we go. Radius of the circle. So that's why we call it a radius. If you think about what is a one-dimensional circle, it's just an interval, right? It's a flat circle. And here, this would be R. Oops, capital R. That should be capital R too. Capital R. And that's really it. So that's why we call it a radius. And what gets even cooler is you can extend this idea to any number of dimensions that you want. So in higher dimensions, the region is an n-dimensional ball of a certain radius. So if you've got a series that has 3 variables involved, now your region of absolute convergence is literally a solid ball in space. And on that ball in space, the series converges. So cool. So cool. Okay. All right. Let's do another example here. So let's find the interval of convergence and the radius of convergence of this series. And for this one, let me see. This one, yeah, I want you all to try this one on your own. So you're going to use the same technique in the example that I just showed you, but think about this for a minute and think about how you would begin. All right, now say something out loud to yourself or to your dog or to your group members or to somebody or to nobody about what you're going to try verbally. Okay, now try to work it out. Try to find the interval of convergence and then find the radius of convergence. If you need a hint, try using the ratio test. Try using the ratio test. All right, now let's work it out together. Uh, what I did here, it looks like the first thing I did was I just kind of massaged the summand a little bit just to point out that this is actually a power series. There's one thing I should say here, which is this stuff only applies when you actually do have a power series. So make sure that the series you're working with has the proper form. In other words, c sub n x minus a to the n, right? Which we do. So in this case, this is c sub n, oops, this is c sub n, and here a is equal to 0. So we're looking at a power series that is centered at 0. All right, we're going to use the ratio test. We're going to look at this ratio and take the limit as n goes to infinity. Get a big old mess here. Remember, like I was saying before, don't let these messes overwhelm you. Just write them down and walk through them piece by piece, and you'll see all the pieces kind of fall off and fall together, right? So after this gets simplified, you get this, which is not too bad. And that simplifies to this. Here I'm just using that standard limit technique of dividing by the highest power variable there. So I divided by n. The only thing that the absolute value bars need to remain on is x, because we don't know x. X could be positive or negative. And then when we take the limit as n goes to infinity, this goes to 1. So this goes to 4x, 4 times absolute value x. All right, so the limit as this goes to infinity is this. Ratio test says this series will converge absolutely as long as this is less than 1, just like so. But if this is less than 1, then absolute value of x is less than 1/4, which means this. So we are guaranteed that the series converges absolutely, absolute convergence, on this interval, -1/4 to 1/4. Remember, absolute convergence is like, we love absolute convergence. Love absolute convergence because we can do all sorts of stuff to the sum and everything works out just right. So we've got really, really nice convergence on this interval. Um, just looking at the interval, we can also see that the radius of convergence is going to be 1/4. Now we just need to test the endpoints. So we don't know what happens at the actual endpoints. That's inconclusive from the ratio test. We know that it will diverge away from those points. So if you're, let me do this right, if you're bigger than 1/4, the series diverges. And if you're less than -1/4, the series diverges. But what happens at those endpoints? We got to test. Here we go. If x is equal to -1/4, then our original series becomes this. And here I'm going to be a little bit clever. I'm going to perform an index shift, right? I'm going to shift by 2. This is actually just a p-series. And this p-series diverges by the p-test because p is equal to 1/3, which is less than 1. So divergent. So it diverges when x is -1/4. If x is +1/4, then our series becomes this. And once again, I apply I apply an index shift. It is actually applied here as well. It's applied there as well. um, and then we get this. So the p is still the same here. The p is still 1/3, but now we have an alternating p series. So we get a little bit more convergence because of the alternation. And in this case, it will actually converge. So this series converges conditionally by the alternating p test. So our interval of convergence for our original series is this. Okay, now what I'm saying is this. Let me go back to our original series. This series converges for any value of x that's between -1/4 and 1/4. including 1/4. So it's a convergent series for all of those values. All right. Do. Okay. Now here's another one, and I want you to try this one yourself as well. Yeah, try it yourself, and then we'll go through it in just a moment here. So think about it for a minute. Right. And then try to calculate it yourself. Try to find the interval and the radius of convergence. All right, and now let's do it together. So, well, I guess the first thing I should point out is that this is actually a power series. So it's good to at least know and verify that you are actually working with a power series. So what I did here was I basically massaged the summand until I got it into the form of a power series. So this is really the power series that we're working with right here. Here's C sub n. The center is 1/2, and that's what the series looks like. All right. Okay, let's use the ratio test again. So it's that same technique again and again and again. Ratio test is applied. Big mess, clean up the mess, simplify some things considering absolute values, and then take the limit as n goes to infinity. This goes to 1, so this goes to this. All right. This is what we're left with. If this is less than 1, then we get absolute convergence. If this is greater than 1, we get divergence. So let's find the interval of convergence here. So the series will converge absolutely, like I said, when this is less than 1. So you go through the algebra here, and you get this. So this right here, this is the radius of absolute convergence. So we're guaranteed absolute convergence there, but we don't know about the endpoints. However, now that we know this interval, we can determine the radius. The radius is just half the length. So in our case, the radius is 2.5, 2.5. Now we test the endpoints. Maybe we'll get a tiny bit more convergence. Who knows? Here we go. When x is -2, I'm going to plug -2 in for x, and our series becomes this, which is equal to this, which is equal to this. That's an alternating p-series, and it converges conditionally by the alternating p-test, because p is between 0 and 1. When x equals 3, the series becomes this, which becomes this, which becomes this, and again, this is a p-series, but now it's going to diverge by the p-test. This is not alternating, right? It's going to diverge by the p-test. So our interval of convergence is -2 to 3 with -2 included. And that's the idea. All right. So on that note, let's play. Let's play. That's your intro to power series. We're going to elaborate on that when we get to section 11.9, and then even more when we get to 11.10. Just a little heads up, 11.10 is a long section. 11.10 is like 45 slides or something. That'll be a long lecture, but that's like the most critical climactic payoff of the course. So we're going to spend at least one day doing just that section because I want everyone to have a deep understanding of Taylor series and Taylor polynomials because they get used all the time. All right. Okay, enough of my rambling. Thank you all again for listening, and I will see you next time. Oh wait, I didn't even do my little goodbye. Here, wait. There you go. Thanks for listening, everybody. I'll see you next time.